Okay, we have just seen how our single diode half-wave rectifier basically replicates what Mr. Fiore has here. We've had a little pause in our recording, and we're going to go back and take a little bit closer look at the difference between why you can get a signal that almost maps your input signal over your load using a diode half-wave rectifier, and sometimes you really do see the effect of the diode's internal characteristics and limits, its forward bias and its bulk. So we're going to take another quick look at Tina. We're going to go back to our real simple half-wave rectifier, and we're going to look at the difference in what our load signal looks like when we use a different magnitude of input signal. So instead of applying a 5-volt peak, we're going to apply a 20. So we're going to make our input signal pretty big in comparison to the forward bias voltage of our rectifying diode. And hit OK. So I just adjusted my input. So this would be the equivalent of adjusting the secondary of your transformer if I were using that to supply my circuit. So I pulled up my transient analysis. Now I'm hiding all the curves for the circuit that I'm not looking at, and wow, now the relative difference in the load output in olive and my input signal is small. So rather than being maybe 10% lower, now the voltage drop over my load, or the voltage applied to my load, is very close in relative magnitude to what I'm applying. Now we've still got that same difference right at the top, and we could probably measure this if we used our measurement tool. See, we've got 19.31 on our load, our olive plot that we're selecting here with our measurement tool, versus the full 20 of our input signal. So there's our forward bias voltage, but in this it's the same absolute value because the diode hasn't changed, but it's smaller relative to what we're applying, so maybe it wouldn't be as much significance in our circuit application. Well, if some is good, more is better, right? What happens if we say, great, I would like this little diode to rectify 120 volts, 60 cycle, coming right out of my wall maybe. So I'm going to try to rectify a typical wall socket grid power output. So I increase the peak voltage of my source up to 120. That's probably a bit higher because it's usually 20, or a bit lower, it's usually 120 RMS. Nonetheless, it's in the ballpark, so I'm going to do that same transient analysis and see what I have. I'm going to hide all the curves I don't want before I look at anything. And oh my goodness, I'm on the forward cycle. I got exactly what I wanted. My input cycle and my voltage over my load is almost superimposed, but good heavens, I'm not getting rectification anymore. That negative cycle is starting to break through, and so the diode is no longer stopping. It's no longer acting as an open with that higher applied voltage. So what in the world could have happened to cause that? The answer might be in the voltage specs. So I can go into my simulator and I can double click on my diode that I selected and go to the type, and there's 3 little dots that show that I can get more information. I click on that and I get a little mini spec sheet. So these are the actual performance parameters that the simulator is using to give me the behavior in my simulation. So it's really simulating a real diode. Now if we remember the characteristics that might be causing this, thinking back to our diode specs, we know that we're getting current breaking through on the reverse cycle that we shouldn't. The diode is not acting the way we want with reverse bias. So let's look and see if we can't find something that would apply in the reverse bias. And we notice reverse bias breakdown voltage. This is that one you never want to exceed. It's 50 volts. Wow. If I read my diode specs, I would have known for darn sure that I shouldn't apply more than 50 volts in the reverse bias, and I applied 120. So this is an example of our simulation actually modeling a circuit component failing. I just melted my diode effectively. So basically this is an example of something you would see in a failure scenario, a troubleshooting. So if somebody is applying a voltage that exceeds the reverse breakdown of a rectifying diode, you might start to see that negative half wave that should be stopped. You may see it coming through in your output circuit, and that would indicate that somebody exceeded the capabilities of a diode. So that's a good troubleshooting tip for the future that we can look at with Tina. Okay, so we've probably covered just about everything important with simple half-wave pulsed DC rectifiers. So let's take a note about our supply voltage before we go on to see what we can do to give ourselves true DC. Right now in Tina, I'm simulating these circuits using just a pure AC waveform, just like your AWG and your picoscope if you're using those for your labs. So I'm basically using a big simulated function generator. In reality, if you're rectifying a signal, very likely you'll be using an AC input from a transformer that's probably coming from the grid. So if you remember back to your studies in AC, a transformer is an electromagnetic device. So we're using a magnetic field contained within something with a high magnetic permeability. It's like some iron, a silicon iron core, to basically convert electrical energy into magnetic and then back to electrical. So we have basically two inductors, at least in a transformer. And one is our primary excitation, and it's coupled to a second inductor with that magnetic field, and that secondary is what we're using to supply our diode rectifiers. So that's our sinusoidal voltage supply in this case. It's the secondary of a transformer. And of course the number of coils in our primary versus our secondary is what determines the voltage ratio between the two. So we can have step up or step down. So that's what we are using for our input. Now we can actually simulate a real transformer with Tina, as well as build one with our in our proto boards if we have a small transformer. But just for simplification, I'm using basically a sinusoidal function that would be coming from a transformer secondary. We'll actually put a real transformer in Tina a bit later. So next step is to see what we can do to give ourselves true DC. And Mr. Fiore discusses this in the smoothing, filtering the output section here starting on page 67. So we're going to introduce the concept of true DC versus pulsed and look at the true DC average level versus what we call ripple, which is the remaining periodic waveform that we may or may not want. So as we mentioned with our Tina output, let's go back to our waveform output here and blow it up a little bit. What we really want, we've got our green curve coming out of our diode, and it comes up and traces our input, but then it doesn't stay flat. It goes back down and then shuts off for a while. So ideally, if we wanted true DC, we want this to stay a flat line. So it's like the diode needs a little help. It can only supply a voltage on the forward half cycle. But if we had something else in the circuit that kind of took over the job of supplying voltage and took over once we hit that peak coming out of our forward bias diode, and then supplied something for a time equivalent to, say 1 period of our waveform, and then by the time our diode was conducting again on that next forward cycle, it would pick up again. So we kind of need to give the diode some help carrying and supplying that forward voltage signal during the times when it's not being supplied or it's blocking the signal. So the thing that we use for that is a capacitor. So this is a schematic here in figure 3.6 of a half-wave rectifier with a smoothing capacitor. So what's going to happen is on our forward cycle, our diode is going to turn on. It's going to flow current both to the capacitor and to the load. The capacitor is going to charge up because it's getting conventional positive current flowing onto it, and there's the little positive telling us it's doing that. So the capacitor is going to end up being oriented with its positive charge in the direction facing the upper half of the circuit. As the negative cycle comes out of our secondary, we basically our input to our diode starts rolling down back towards zero. The capacitor, if it is fully charged, will now have a voltage that was equal to the peak coming out of the diode and hence from the secondary. So it will act as a voltage source. As long as it's got enough charge to keep supplying that, it will. And the reason it doesn't discharge, it can discharge through the load, it can't discharge back through the diode when the transformer supplies the negative half cycle, as it's in reverse bias. So it can't discharge back through the diode and discharge itself through the secondary coil because the diode becomes an open. So the capacitor can charge from the diode, it can't discharge from the diode, but it can discharge through the load and act as that voltage supply that we needed between peaks. So this is great. We just slap a capacitor in this position across the load in parallel with the load, so it becomes a little voltage source when the diode is not supplying the peak voltage we want. Now the only question left is, how big of a capacitor do we need? And thank goodness we studied RC time constants back in our DC course, or assuming you did. So we know that the time constant of an RC or an RL circuit is related to the time it takes for a signal to decay to some value of E, 1 over E. But it gives us an idea of basically how long it takes for a signal to decay. So we can compare the tau of our RC circuit, which we basically have here. When the diode is no longer supplying peak voltage, this capacitor takes over and it's discharging through the resistor. So we've got a little RC circuit going here between peaks from the diode. So it'd be kind of nice if we could time this thing so its tau was somewhere on the order of the time between these peaks. So we want tau to be something close to this peak to peak time, which is, oh, how convenient, the period of the input waveform. I know the frequency, I just inverted, I get the period. Well, chances are my load is fixed. It's some circuit I'm powering. So it's 10 ohms or it's 100 ohms or something. And if I know my frequency of my secondary, I can say, okay, let's pick a tau that's equal to the period of the waveform coming out of my secondary. I know my load. I know tau equals RC. I can pick a C that's going to get me in the ballpark, and we can plug it in and give it a try. So let's pull up Tina again and see how that works. So this time I've got a little bit more complicated circuit here, our second one that we've been blanking out the output in our transient analysis. Now we're going to do the other. So I have the same kind of diode. So we're not going to apply a big voltage to it and burn it out this time. We're going to respect our reverse bias max voltage limits. And we have a 10 volt peak, 60 hertz input signal, so we're going to pretend this is coming from the secondary of a transformer. And we're going to double click on this and just make sure that label is correct. Our amplitude, yep, 10 volts, frequency 60 hertz, yep, it's what we want. And we have a load, and it's labeled as having a 100 ohm resistance. We can check on that. Yep, it's 100 ohms. Okay, so this is the R and our RC of our time constant. Here's our capacitor, and right now it's 1 millifarad, so it's a pretty big capacitor. And in here we've got a little 1 ohm resistor, and this is a measurement trick. We can use Ohm's law basically to give us a current measurement without having to put an ammeter in here. This is acting as a shunt resistor. So this resistor is actually like a little ammeter. I have a voltage measurement point at C that's measuring the voltage drop over my 1 ohm resistor. So the current in amps flowing through this resistor is exactly equal, because the resistor is 1 ohm, to the voltage drop over it. So my voltage C relative to ground that's going to plot out when I do my analysis is going to literally tell me the current flowing through this resistor, which is also the charging current of the capacitor. I'm going to get positive current coming out. It's going to pile a bunch of positive charge on this plate of the capacitor. There's going to be basically negative charge accumulating on this side, which means when my current's changing, my voltage is changing, I'm going to get current flowing in this direction to ground as the capacitor charges. The capacitor, it'll go the other way when it discharges, and of course it can't discharge back through the diode. So we can run our transient analysis and see to what extent this capacitor is doing a good job supplying voltage to the load between peaks. And we can look at our RC relationship. So we can start with our 60 Hertz, and the nice thing about our transient analysis is we already got an idea of the period we need. So 1 over 60, about 20 milliseconds would be appropriate for one period. In case we didn't call it quite right, we can display that. And we still have our, turn off our old circuit. And now we have to rescale a little bit, but that's okay. We can go to our output and we can rescale. We can go from a lower limit of 0 to an upper limit of 10, which was basically what we wanted. Now let's rescale it a little bit for better visual clarity. We'll go from -1 to 11 maybe. Okay. So let's put up our legend just so we keep things straight. So our blue waveform is our input. So we have our 10 volt coming in, 10 volt peak, and let's look at where we put our test point B. So point B is the voltage drop over the load, and then C is basically the current in amps over our capacitor. So let's see what happened. So we turned on our circuit and we supplied the first half cycle of our signal out of our pseudo transformer secondary with our voltage source. It came up and it started charging the capacitor. We can see that with our plot C, and at the same time it was supplying voltage to the load, so it was supplying to two things. So our secondary was opening our diode, and then we flowed current and piled up some charge on our capacitor, which we can see with this red plot, and we supplied current to the load. And so we had a voltage drop over the load that traced the input just like we wanted it. And it rolled off a little bit, but at this point, we'll get our marker. At this point, the capacitor took over and supplied voltage to our load, and you can see it's decaying very slowly. So we've got a nice long time constant in our RC circuit. So we picked a good sized capacitor for our resistor, and we could redo our analysis, show the next cycle and how we're picking up just on the back end of the next forward cycle. So if we were to look at just what the resistor sees, just what our load resistor sees, we'll clear. No, we don't want to save. Let's rerun our analysis with a couple of periods, maybe quite a few. Let's do a 60 millisecond transient analysis and display several periods of our input waveform. and we'll just take the ones we want. And in fact, we're only going to plot B, which is our signal over the load. We're not even going to plot the source, as we only really care about the signal over the load. Let's make sure B was in fact the one we cared about. Yep. Close. And Tina has unfortunately made an annoying scale change, which we can reverse, no problem. We can go from 0 to 10 like we'd like, and here we go. Here's our output over the load. This is what our load circuit sees. So it sees the first part, it comes up with our first forward cycle being passed by our diode, and it just clips the top of that peak. It rolls down, and then the capacitor catches it and starts discharging, and this long descending line is the RC discharge curve of our capacitor and load resistor. So the capacitor is discharging through the load resistor, and it discharges down to about 7.5 volts before we have the next positive half cycle, and the diode is now conveying current. It's open and it's showing the voltage signal from the secondary. We come back up and the same thing happens again and again. So just to show, try to point this out here. So the difference between our peak and this little valley, this low point in the RC discharge, this is our ripple. So this is the variation in voltage that our resistor is seeing. And either the bottom or somewhere midway there would be considered our true DC level. So the average time invariant signal that we're getting. So we can see that the load is always getting, around and about 7.3 volts. So it's seeing a steady 7.3, but then there's this, call it 2.5 volt time varying signal that's superimposed on top of it. So that time varying signal of 2 volts is the ripple. If we wanted just true DC, we wanted that ripple to be smaller, we can adjust our tau of our time constant a little bit more, make it bigger, make this slower to discharge, so we could go with a bigger capacitor. Eventually we're going to reach a limit because the smaller this resistor is, the faster the capacitor can discharge. The two work together, obviously. Tau equals R times C, and our load is usually set by the needs of our external circuit. But just for fun, let's go ahead and double that, or take it up to say 5 millifarads, and let's rerun our analysis just to experiment. And unfortunately we will have to go through our rescaling again, but that's pretty quick since we know where we want it this time. And this is the fun of simulations. You can basically build a whole bunch of different circuits very quickly and adjust components. So unfortunately that did not quite get us where we wanted to in the first few cycles. But you'll notice something. We do have a flatter line between, and it's changing from period to period. If we were to go ahead and display our charging, go back to the chart. This is the charging current through that capacitor. By going to a much bigger capacitor, what we did was we gave it more capacity, literally, to hold charge. So it didn't get all full on the first cycle. So it couldn't supply as much voltage to the load on that first cycle. But as we go cycle to cycle, it's getting more and more charge and requiring less to give itself a full charge each time. So if we were to redo this analysis and give it a few more periods, and go back and display, and we'll show both the capacitor charging current and our load this time. And we'll see that basically we get to a point where the capacitor charges as much as it's going to, and now it's holding the load with a much higher average DC voltage. So instead of 7.3, it's now at 7.9. So it's still not getting us all the way to 10, but basically the ratio between the true DC and the peak to peak and the ripple is now less. So we got better, but not perfect. So to get perfect true DC, we have to have a little bit more complicated circuit that is beyond the scope of this class now, but hopefully this gave you a little bit of appreciation for just how rare and precious a thing that true DC is, and the utility of electrochemical storage and other devices that can provide true DC. When we go into our next section, where we'll go into bridge rectifiers and full wave rectification, we'll see that we make our job much easier from the standpoint of smoothing and creating DC. And so hopefully this will give you an appreciation for why bridge rectification is worth the extra 3 diodes. So that is it for our rather long lecture on half wave rectification and smoothing. And so with a little bit of a dive into the fun you can have with Tina and circuit simulation, and in our next lecture we'll pick up full wave rectification.